Welcome back, everyone, to AI Paper Podcasts. This time, we're taking a look at a paper that's a real head-turner in the AI world.
Yeah, this is a really exciting one. Really challenges some assumptions we've had in the field.
It really does.
For a while.
Exactly. Yes.
So let's dive into it. So this is Scaling Language-Free Visual Representation Learning.
Okay.
It's by David Fan and a team out of FAIR, Meta, and NYU.
Oh, wow. So a pretty strong group of people working on this, then.
Really, really top-notch researchers.
Yeah.
And the central finding here is that purely visual self-supervised learning.
So vision only.
Vision only.
No text involved.
You got it.
Okay.
Is hitting performance levels.
Interesting.
That are actually rivaling CLIP.
Whoa. Okay.
Which, for folks who aren't familiar, CLIP is sort of the
king
of hill when it comes to contrastive language-image pre-training, particularly in multimodal tasks.
Right.
So thinking about things like visual question answering, or even like cracking OCR.
Which traditionally we've thought of as having to involve language, right?
You would think so.
Like, how can you possibly understand text without having been trained on text?
Exactly. And they're even doing things like understanding charts and all this without any language data.
So purely from the visual side, they're somehow understanding these high-level concepts.
Yeah, and this really raises the question, right?
Yeah.
Is it the language that was the secret sauce for CLIP all along?
Right.
Yeah.
Has it been the data?
Has it been something about the data?
Exactly. Yeah, because they trained on huge data sets, right?
Massive data sets.
Yeah.
So to really dig into that question, the researchers designed a very clever experiment.
Yeah.
They trained visual SSL models,
Right.
primarily focusing on Dino V2, and they also took a look at MAE alongside CLIP models, trained on the exact same massive data set of web data. This is MetaCLIP. It's got 2 billion image-text pairs.
Huge.
Now, of course, for the SSL models.
Yeah.
They're only using the image component of that.
Makes sense.
Yeah.
Can't give them any text.
Exactly. Can't give them the text. And then to evaluate this, this visual encoder, they use the Cambrian 1 VQA Suite.
Interesting. Now, that name rings a bell.
Yeah.
But remind me, what is that exactly?
Cambrian 1 is this really interesting benchmark.
Okay.
It's super diverse.
Okay.
It's got 16 different task categories.
Whoa.
And the idea is to really push these models.
Right. Push them to their limits.
Yeah. And see what they can do.
Really get a comprehensive view of their capabilities. Not just on one narrow task.
It's not just like, can you classify this image?
Right.
Yeah.
It's, can you answer all kinds of different questions about images?
So it's a much more holistic view of the model's understanding.
I like it.
So the big takeaway here for folks tuning in for the quick version.
The TLDR.
Is this, so visual SSL. When you scale it up to this level, when you train it on this kind of data.
With enough data.
Can go head-to-head with, and in some cases, outperform the language-supervised methods.
Wow, that's pretty incredible.
Really?
To think that just from the visual side, you can get to that level of understanding.
Yeah, really impressive.
Yeah, okay, so let's dig in a little deeper here.
Absolutely.
We talked about this multimodal gap.
Right.
And for a while now, visual SSL has been, great at image-specific tasks.
I'm really good at
like object recognition.
Classifying objects, segmenting images.
Right, but all that good stuff.
When it comes to multimodal stuff, really falls behind.
It's struggled.
Yeah.
And especially on VQA.
Right, so this is where you have to understand the image and some text.
And answer a question about it.
Yeah.
Exactly. And the thinking has always been, well, it just doesn't have that language grounding.
Right, that was the assumption.
CLIP has that edge.
CLIP's got that secret weapon.
You got the text. And so, of course, it's going to do better.
Yeah, makes sense intuitively.
It does.
Language provides so much context and meaning that maybe the visual signals alone just can't capture.
Right.
Especially if you're thinking about, okay, what does this text in this image say?
Yeah, or even just like relationships between things.
Right, more complex relationships that are often described with language.
That we would use language to describe.
Yeah.
But the researchers here, they said.
They focused on.
Hold on. Yeah. What about the data?
The data. What about the data?
Right.
Because CLIP's been trained on these massive scale data sets of paired images and text.
Yeah.
Billions of examples.
Right, billions.
And SSL has been using large data sets, but
ImageNet.
Right, ImageNet or other image-only collections.
Yeah.
Not quite the same scale.
Right. Right.
Not quite the same diversity.
So maybe that's the real...
Maybe that's the missing piece.
Yeah, the missing ingredient.
Yeah.
Okay, so how did they go about testing that?
So they did something really, really clever. They trained both their visual SSL models,
okay,
primarily Dyno V2, and again, that learns by identifying similarities between different views of the same image.
So sort of like a contrastive learning approach?
Kind of a self-supervised contrastive learning.
Yeah, okay, got it.
And CLIP on that same MetaCLIP data set.
Okay, that huge...
The massive one, 2 billion image text pairs.
Right, so they're controlling for the data now.
Exactly, controlling for the data.
Both models see the same data.
No, just the images for SSL, of course.
Of course, right.
And then they use that Cambrian 1 suite to really rigorously test these encoders.
Okay, so they've got the same data.
Same data.
Different training objectives.
Different training objectives.
One with text, one without.
Exactly.
And then this really diverse evaluation suite.
And Cambrian is key here.
Yeah.
Because it covers such a wide range of VQA tasks.
Okay, so walk us through the different categories.
Yeah, so we've got general VQA,
okay,
which is like those everyday visual reasoning questions like
what color is the car?
Exactly. What color is the car? What's happening in this image?
Okay.
And then there's knowledge VQA.
Okay.
Where you often need information that's beyond just the image itself.
Ah, so it might require some external knowledge.
Yeah, like you might need to know which famous landmark is in this photo.
Okay.
Right.
Interesting, interesting.
And then, for this paper particularly, we're looking at OCR and chart VQA.
Right, because that's the surprising part.
That's where things get really interesting.
Yeah.
Because that's testing. Can they understand text?
When they've never seen it.
When they haven't been trained on it.
Yeah, yeah.
Can they interpret these charts and graphs?
Okay.
And then finally, you've got vision-centric tasks.
Okay.
Which are really focusing on those core...
Like lower
level visual perception, reasoning ability.
So things like
edge detection.
Edge detection.
Yeah, or
like segmentation, that kind of
segmentation, exactly.
Okay, got it.
So by using this, they get this really broad,
really comprehensive
picture of what these vision encoders can do.
Okay.
All right, so let's dig into what they found when they started scaling these models.
Okay, so this is where they really cranked up
the
size and the data.
The size, the data, the whole 9 yards.
Yeah, so let's start with the model capacity.
Okay, so they trained a series of these WebDino models ranging from, 1 billion parameters up to a massive 7 billion.
Wow.
So we're talking huge models here.
Huge models.
And they noticed this really interesting trend. When they scaled up the model, the average VQA performance improved.
Okay.
Almost linearly.
Oh, wow.
On a log scale.
So as the model gets bigger, it just gets better.
Yeah. Bigger model, better performance.
Across the board.
Across the board.
Interesting.
They saw this on the average VQA, but also specifically on OCR and chart.
Okay, so even on those.
Even on those.
Text-heavy tasks.
Exactly.
More parameters means better performance.
Yeah, more is better in this case.
Okay, and how did that compare to CLIP when they scaled it?
This is where it gets really interesting, right?
Yeah.
So CLIP sort of plateaus after about 3 billion parameters.
Interesting.
It's like it hits a ceiling.
Right, right.
It's not getting those same gains.
So it's like early on, CLIP might be more efficient.
Yeah, maybe more data efficient.
You get more bang for your buck, but then you just stop.
It hits a wall.
While these SSL models
just keep going.
Just keep scaling.
Yeah, fascinating.
Yeah, it's like there's some fun dimensions.
It's unlocked.
Yeah, it's unlocked some
through a billion
potential.
Yeah.
That CLIP just doesn't have.
Yeah.
So early on, CLIP was better.
CLIP did better.
Especially on the OCR and chart.
Yeah.
Which makes sense.
Right. It had that language.
It had that language advantage.
Yeah.
But the SSL models were better on the vision-centric tasks.
That's right. Yeah. Right.
Yeah. So maybe they're learning something different in those early stages.
But then as they scaled, that gap closed.
Gap closed.
And eventually, CLP's on average VQA.
Average VQA.
When you get to those really big models.
5 billion and above.
Yeah, the 5 billion, the 7 billion parameter models.
Wow. So it just shows the power of scale, I guess.
Yeah, scale the data.
And maybe we shouldn't underestimate purely visual learning.
Absolutely.
It can do a lot.
It can. It can.
More than we thought, maybe.
Yeah, maybe more than we thought.
Okay, so we talked about scaling the model.
Yeah.
But what about just giving it more data?
Yeah, what if we just...
Even without making it bigger.
Just keep feeding it data.
Right, exactly. So what happened there?
So they took their biggest WebDino model.
That 7 billion parameter one?
Yeah, the VT7B.
Okay.
And they trained it on increasing subsets of MC to B.
So starting with 1 billion.
1 billion images.
Going all the way up to 8 billion.
8 billion, yeah.
Okay. And how did the performance change?
So on those general VQA tasks and knowledge VUA, they saw improvement as you added data.
Okay.
But it kind of leveled off.
Oh, so like diminishing returns?
Diminishing returns.
After a certain point.
Yeah, after a while.
Adding more data doesn't really help as much.
Not as much.
Vision-centric also improved a lot early on.
Right.
And then kind of plateaued.
Yeah, plateaued.
Okay.
But
OCR and chart.
Different
story.
Kept going up.
Oh, really?
Yeah.
Interesting.
So it seems like that ability to
really understand text.
Like
charts.
Really benefits from seeing more examples.
Seeing tons of examples.
Yeah.
Even without the explicit labels.
Right. It's just something about the sheer
volume. Diversity of the data. Helping it.
Yeah, it's picking up on something.
Okay.
And what's really interesting is even when you compare models trained on the same number of samples.
Okay.
WebDino consistently beat out CLP.
Oh, wow.
On average VQA.
Well, even when CLP had the same amount of data to learn from.
Same amount of data.
WebDino was still better.
WebDino still pulled ahead.
Okay.
And then, by the time WebDino had seen 8 billion images.
8 billion, wow.
That had closed the gap with CLP on those OCR and chart tasks, too.
Oh, wow. Okay.
So, again, suggesting that
it's got this scaling potential.
There's this untapped potential.
That CLIP might not have.
Yeah, might not have.
Interesting. Okay. So we've seen that Dino V2 benefits from scaling. Both the model size and the data. But what about other SSL methods?
Right. Is this just a Dino thing?
Yeah. Is this just a quirk of Dino?
Yeah.
Or is this a broader phenomenon?
They wanted to check that out, too.
Okay.
So they also trained some models using MAE.
Ah, MAE. So that's the...
Yeah, this is the masked autoencoder. Approach.
Right, so it's trying to...
you basically mask out part of the image.
Right.
And then have the model reconstruct it.
Yeah, like fill in the blanks.
Oh,
right.
So they trained these MAE models.
Which they called WebMAE.
Okay. On that same MC2B data set.
Right, keeping that consistent.
Right. And they scaled them up to 5 billion parameters.
Yeah. Okay, and what happened?
Similar trend.
Okay.
Average VQA performance went up as the model got bigger.
Okay, so we are seeing some generalizability here.
Yeah.
It's not just a Dino thing.
It's not just Dino, but there are some interesting differences.
Okay.
So WebMAE was really good at those OCR and chart tasks.
Interesting. So even better than
WebDino on those specific tasks.
Huh. Okay.
Across all the model sizes.
Okay, so different models, even when trained on the same data, might have different strengths. Different weaknesses.
Yeah.
So the choice of method still matters. Right?
Yeah, it influences what those visual features...
All to learning.
Yeah, what it's learning.
What it can do.
Okay, so we've seen that this web scale data seems to be really important.
It seems really important.
But did they try training on smaller data sets just to see
what would happen?
Yeah, as a comparison.
Yeah.
So they took their WebDino models at 1 billion, 2 billion, and 3 billion parameters.
Okay.
And they trained them on the classic ImageNet 1K.
Right, which is much smaller. And less diverse?
Less diverse.
Yeah.
And they just used a standard SSL recipe there.
Okay.
Nothing fancy.
Yeah.
And then they compared their performance on VQA and ImageNet linear probing.
Okay, remind me what linear probing is.
So linear probing is...
I always forget.
You basically train a simple classifier on top of those learned features.
Right.
To kind of see how good those features are.
Okay, yeah, I remember that now.
Yeah. And they compared all that to the models trained on MC to B.
Okay, so the big data versus the...
Big data versus small data.
Small data. Yeah. What did they find?
Pretty clear results.
Okay.
Those ImageNet models just didn't perform as well.
Okay.
Across the board.
Across all the tasks.
Yeah, all the metrics.
And they didn't really scale either, right?
That's the key thing.
Yeah.
They didn't show that same improvement.
As you made them bigger.
Yeah, as you made them bigger.
It was like they hit a ceiling.
Yeah.
Right.
Not enough data to really
take advantage of those extra parameters.
So it's not just about big models.
Right.
it's about the data, too.
It's the combination.
It's the combination.
Yeah.
It's like...
You need both.
You need both.
Okay.
And this is something we've seen in NLP, too, right?
Right. With the large language models, it's all about...
Data.
Scale and diversity of the data.
Absolutely.
Yeah.
Really driving those impressive results.
Okay, so...
Yeah.
They focused a lot on VQA.
Yeah.
But they also wanted to see how these models did on more traditional vision tasks.
Yeah, the bread and butter stuff.
Right, exactly.
So they tested them on ImageNet classification, semantic segmentation on AV20K, and depth estimation on NYU Depth V2.
Okay, so a good range of...
Yeah, a good mix of...
Different tasks.
Yeah,
and how did they do?
So performance did generally improve.
Okay, so scaling still helps.
Scaling still helps.
Yeah.
But it wasn't as dramatic.
As with VQA.
Yeah.
Interesting, okay.
And they got some really good results, outperformed MetaCLIP.
Oh, wow.
Competitive with off-the-shelf Dino V2.
So they are learning general visual features.
They're learning good features.
Yeah.
But it seems like VQA is maybe a better test.
More sensitive.
Yeah, more sensitive.
To those improvements.
To those improvements in understanding.
Yeah, that's more complex, right?
It's a more complex task.
It's not just like, is this a cat or a dog?
Yeah, there's more reasoning involved.
Yeah.
Okay, so one of the most surprising things to me.
Was...
This was a surprise.
How well they did on the OCR and chart.
Yeah, totally unexpected.
Because SSL has never been good at that.
Historically, it's been pretty weak.
Right, you would think you need...
You'd think you need the text to learn how to do that.
Yeah.
But somehow, these models, when they're scaled up on this web data, they're doing really well.
It's wild.
Yeah, so the question is...
How is this...
How are they doing this?
Yeah.
So the researchers have this really interesting hypothesis.
Okay.
They think that it might be because these web-scale data sets just have a lot of text in them anyway.
Oh, that's interesting.
Yeah.
Yeah.
Because if you think about it, it's not like ImageNet where it's
all carefully curated.
Yeah. Object-centric images.
Here's a cat.
Here's a cat. Here's a dog.
Here's a car.
Right. The web is messy.
Yeah, it's the Wild West. You've got text everywhere.
Text everywhere, like on signs,
labels, watermarks.
Yeah. All sorts of stuff.
And so maybe these models are just kicking up on those paths.
Even though they're not explicitly
telling them
told what the text is.
This is text. This is what it means. It's like
they're learning by osmosis.
Yeah, they're just absorbing it from the environment.
Yeah. Okay, so how did they test that idea?
So they used this model called Small VLM2.
Okay.
It's a multimodal large language model.
Okay.
And they used it to filter their data set.
Okay.
So
to find images with text. Okay.
And they created 2 filtered subsets.
Okay.
So the first one was a light filter.
Okay.
Basically just any image with readable text.
Okay.
And that was about 50% of the data.
Okay.
And then they had a heavy filter.
Okay.
This was much smaller.
Okay.
Only about 1.3% of the data.
Wow.
And that was just images with...
Just charts and documents. So charts, tables, documents.
Really text heavy.
Okay. And then they train their models on these subsets.
Okay.
So
Same model.
Different data.
Recursive data.
Different flavors, yeah.
Okay, and what happened?
So even that lightly filtered data, the one that just had more text in general, improved OCR and chart performance by over 6%.
Wow.
Compared to the full data set.
Okay, so just having more text presents.
More text.
It seems to help.
Yeah. And it didn't hurt performance.
Okay.
On the other tasks either.
So it wasn't like it was overfitting.
It wasn't like it was too specialized.
Yeah.
Yeah. Okay. But then that heavy filter.
That tiny 1.3%.
Yeah. The tiny subset. Yeah. That model.
Yeah.
Blew everything else out of the water.
Oh, wow. Okay.
So not only did it outperform the full data model.
Okay.
It actually beat CLIP.
What?
The language supervised CLIP.
That was trained on all the data.
Okay. By over 4%.
On OCR and chart.
So
a model trained on
a tiny fraction of the data. But very specific data.
Yeah.
Outperformed.
A model trained on all of it.
All the data.
Wow.
Yeah.
That's crazy.
It really is.
Okay, so it's not just the volume.
It's not just the volume.
It's the composition.
It's what's in it.
Yeah, the quality of the data. Okay, so that suggests that even without explicit text, these models can still
learn to understand it.
Learn to understand text just from the visual patterns.
Just from the visual patterns.
Which is mind-blowing.
It is, yeah.
It's like they're developing some implicit understanding.
Implicit understanding.
That language.
Just by looking.
By looking at the
white picture.
Yeah.
So the researchers wanted to see how aligned they were with language. Yeah, so they did this really cool analysis.
Okay.
They took WebDino,